Thank you for being here. And now we have Daniel.
Hi, everyone. I'll be filling in for Ventali today. I think she was on the program. I'm here with the Lita Foundation, and we'll be talking about Valida, our zero-knowledge virtual machine, and how we're using it to push the performance and usability of zero-knowledge proofs. Is this the, how do I click? Uh-oh. Is this the clicker? Am I doing something wrong?
It should be, but it's not plugged in.
Oh, yes, of course.
Ah, lovely. Just 2 seconds. Always the third.
It's a spin manifold. Set up. There we go. Great. So yeah, here's an outline. We'll be talking about virtual machines in general, some of the different types, some of the limitations with some of the other virtual machines on the market today, as well as what we've done at Valida to create the fastest VM out there, and a little bit about the future. So the motivating question is, how do I prove succinctly and in zero knowledge that a given program was executed and that gave the correct result? So importantly, this is supposed to be a universal thing, right? A zero knowledge virtual machine will be a zero knowledge circuit that can prove the execution of an arbitrary computer program specified in some given language. The key properties we need are succinctness and zero knowledge. Succinctness, proofs are not too long, can be said differently in the context of a virtual machine, that it should be much faster to verify the proof than it is to run the actual computation. Zero knowledge, this is the key property for privacy, right? The proof should reveal no information on the internal states of the machine in the course of running the computation. So this would include any private inputs such as secret keys or transaction amounts, account addresses, something like that, that you would use inside of the machine. These are wonderful pieces of cryptography that are really pushing the space forward. However, right now, zero knowledge has these two major problems. One is that it's a technical subject. A lot of the tooling, even that's supposed to be developer friendly, it still has a pretty steep learning curve, as well as the proofs themselves are large and, they're not large. That's the key property. The proofs take a lot of time, space, and energy to create. So even though they're really fast to verify, the cost is, when making the proof yourself, it takes a lot of time to do so, right? So we hope one day that we could do something like generating these proofs, totally client-side on your phone or something. But this is a challenging thing to do. Right now, this tooling is rather slow. So here is a wall of text on some of the different high-level approaches to creating these virtual machines. So maybe ignoring some of the details on the slides here, but the big idea here is like, what do we mean to specify a computer program, right? Everything from C to Magic the Gathering is Turing complete, so the property of being universal isn't very specific. And there's sort of two ends of the spectrum here. One would be to have a domain-specific language. A well-known example of a project that does this is Cairo, and this can be thought of as a sequence of macros that lets you create zero-knowledge circuits directly. This is good for sort of fine-tuning of performance, but is bad for the difficulty of use, as well as it's a little bit harder to reason about the mathematical correctness. So this is a common dichotomy in programming outside of the zero-knowledge context, where low-level languages let you get performance really correct, and high-level languages let you specify the correctness of execution at a level that's easier to reason about. And the approach we take with Valida is this third one. So here we define a virtual machine with an instruction set architecture. like an actual processor has. Ours is extremely simplified, so only a very small number of instructions. And we compile from high-level languages to this, and then this is what we actually implement in zero knowledge, the state transitions, memory loading, and stuff for the virtual machine itself. And we hope that ZKVM will be the dominant way in which developers will use zero knowledge, and this will help with increasing productivity as well as avoiding security flaws. Zero knowledge is a complex subject. There's a lot of difficult cryptography involved, and we don't want everybody who's building a privacy application to have to start from scratch and do this. So with the ZKVM, you can write your code in a language of your choice, compile it, run it, and prove it in zero knowledge. And so you can get all the benefits, both the privacy and the scalability coming from zero knowledge without needing to do the cryptography yourself. So this is a crowded space right now. There have been a lot of VMs just this year. However, we think that many of them have some real problems that we're trying to solve. As I mentioned on the previous slide, a lot of these use a domain-specific language that has a steep learning curve for developers, both in terms of the language itself and sometimes things like you have to have absolute bounds on number of repetitions in a loop. Memory is structured in an unfamiliar way. So it's not just a superficial difference in the language, it's actually a really unfamiliar programming paradigm. Also, several of the other virtual machines out there have claim to be open source, but then have closed source components, for example, proof aggregation or generating the constraints for the virtual machine itself. Another thing that is really important is to have built-ins. You can think of like the Ethereum precompiles, but in the ZK setting, for cryptography operations like signatures or hashes, as well as blockchain operations like EVM transactions. And finally, the sort of most important thing that we're trying to solve is that many of the virtual machines that exist today are still not nearly performant enough to be able to be used at a large scale. And some of the reasons for this are the design of the machine itself is not tuned for optimum performance in zero-knowledge circuits, but rather for familiarity or using a instruction set that exists in ordinary electronic computers. Finally, we want to make sure everything is very extensible so that there's been a new crypto paper on this subject like every 2 weeks that changes everything. So we want to be able to keep pace with these advances. So extensible, performant, and developer friendly. Here's a kind of schematic of how we went about this. So we start with the cryptography, choosing a proving system that has the optimum set of trade-offs. So there's generally a trade-off between proof systems that have really small proofs and proof systems that have really fast provers. And there are some tricks for combining those. Then the virtual machine itself is, we call it ZK-friendly instruction set architecture. So we take a really small, really simplified model of a computer processor, and we compile everything to that. So an important part of this process is step 3, to create good compiling tools that let you take a program written in a high-level language like Rust, high-level in this context, and have something that can be proved in our system. So this kind of lets us have our cake and eat it too, with the choice on one of the previous slides that we use a instruction set that's tailored for zero knowledge to give us really good performance, but then we also create the necessary tools so that developers don't need to use anything unfamiliar to work with it. Finally, these last 2 steps are a little bit more forward-looking, but we want to have use hardware acceleration ranging from GPUs to maybe FPGAs or ASICs one day to really boost the performance as much as possible. And then finally, we want to use formal verification for all the key steps in the process. The idea is that this zero-knowledge virtual machine might one day be the main engine that powers some large-scale zero-knowledge roll-up or blockchain that could potentially have a whole lot of money on it. So we want to make sure that every key cryptographic piece of it is not just audited, but formally verified in the sense of formal theorem prover like Lean. Okay, I'll say a little bit about the design, some of the choices we made to get the performance that we have. So we can think of this virtual machine as sitting in between a prover and a compiler. So the compiler takes high-level language, spits out something that our virtual machine understands, and then the virtual machine creates a set of constraints, some mathematical model of computation that's far away from how you normally think about it, and this is what's actually proved cryptographically. So a key part here is to make sure that we use the most efficient instructions possible. For example, we have special instructions to do finite field arithmetic in our instruction set, and we remove most of the registers to simplify the CPU itself. And then on the compiler side, we have to replace calls to instructions that we don't have with sequences of equivalent ones that we do. So at a high level, we divide our system up into a set of chips. So we have the main processor, one for memory, one for binary arithmetic, as well as a couple more specialized ones here. And then the cryptography underlying it is Starks, and specifically Starks over a small 31-bit field. This is a schematic of what I just said. So here's what we're proving. We separate read-only memory for the program. It's a Harvard architecture. You can't edit your own code. A big RAM and input-output. And these communicate through a series of buses with this set of chips, each of which is a separate zero-knowledge circuit. So we do not have any general registers. The only registers we have hold the program counter and the frame pointer. So these tell us where the instruction that we're about to execute is, as well as where the local variables are stored. We can address RAM both in relative and absolute modes. Can't address ROM at all. So this is a very different construction than you usually have with an electronic computer. And that's because there's no notion of fast versus slow memory in zero knowledge. Right? In an actual physical circuit, then you want to avoid addressing main memory as much as possible, use caches, use registers, because they're orders of magnitude faster. And that concept just doesn't translate here. So the notions of processor that work in the general electronic model are not the right ones to use for zero knowledge. Yes, a little more about this. We don't have a stack pointer. So our stack frames are constant size, and anything that doesn't fit in that just go onto the heap, which again is really no more expensive to use than anywhere else. So when using the VM, you'll first run it through the execution engine. So this is the actual virtualization. You take your software, you run it, and you record an execution trace, so all the intermediate values used to generate the ultimate value of the computation. And then you prove that you have this execution trace. This is the cryptographic part. And then this proof is succinct and can be verified cheaply later on by anyone, for example, on-chain. One key thing that makes our system fast is that we use this baby bear field. It's a 31-bit field. And because it's very close to a power of 2, the arithmetic in this field can be done really quickly in actual physical hardware. You need to constantly be reducing mod p, and doing that is easy because p is very close to a power of 2. However, this field is too small for cryptographic security, so the actual cryptographic challenges come from an extension field. And then the system that we use to commit to polynomials, the core cryptographic primitive is Fry. This is what's used in all Stark systems and is really by far the fastest polynomial commitment scheme out there today. So when our execution trace is separated into one for each chip, each of these is a separate zero-knowledge circuit. And then we later prove the correct execution for each chip. And then later on, we prove that the chips have compatible views with one another so that for example, the processor chip and the memory chip have the same view of all of the loads and stores. Then to actually do this cryptographically, we represent these vectors as polynomials using interpolation, commit to these polynomials, and again, with this, we do what's called a permutation argument for this compatibility check. So given all these single variable polynomials, one representing each sort of column, each variable over time, we combine them in a constraint equation to get a single polynomial, and then we show that it vanishes on the correct domain. So this is the setup that is used sort of throughout the zero-knowledge literature. So maybe let me not say a whole lot more about that. One key fact is that we require constraints to have degree at most 3 because constraint degree is a large driver of cost. Again, we're using this baby bear field. We might one day be able to use the Mersenne prime field using some recent advances in the Stark literature. This field has even faster arithmetic because it's literally just 1 off from a power of 2. A main part of our project is the compiler as well. So we can compile from LLVM to our specialized instruction set. Here's a schematic on what that compiler pipeline might look like. But again, right, we use ordinary programming languages, ordinary compilers to generate the LLVM intermediate representation. This is something you can do with the compiler that's already on your machine for your language of choice. And then we have a series of further optimizations before we get the thing that we actually prove. So here's our GitHub. You can download it now. You can write your own chips and have them generated at compile time to get a machine that has the exact operations that you want optimized. And everything is fully open. We welcome outside contributions. We have an Apache MIT license. And I think I won't have time for this demo. Here's a little mock-up of what the developer interface might look like. So something like GitHub Pro, but in zero knowledge. We have an early access program, so if you'd like to build with Valida right now, all of our code is on GitHub, and we would absolutely love to talk to you to support integration. We're hiring across, as everyone is, cryptography compiler engineers, as well as product people, and not necessarily employee open source contributors. Here's our contacts. I'm Tesseract. Our founder is Ventali. We'd all be really happy to hear from you.
Awesome. Thank you so much. We can leave this one up. And if we can have the lights up. And do we have any questions? We're good? All right. Well, thank you again, Dan. We really, really appreciated it. Yay.
Thank you.
And so that is the end of the programming at this stage. You can still head downstairs for the conversation about regulation and innovation. And then after that, there will be a debate about scaling. So.